In this video, we're going to talk about um, radiation measurement, section 5.3 of chapter 5. Um, so here you can see that to measure radiation activity, they're using a Geiger counter. Now, a Geiger counter is an instrument which what happens is it has some kind of um, an unreactive gas in there, like argon, okay, a noble gas, and radiation, the surrounding radiation will react with this gas and ionize it, okay. So once you create ions, you're creating charge, and charge is the flow of electrons, and that creates electricity, which then gets converted into, so the radiation is getting converted into electrical units, and that is registered as a series of clicks. That's how radiation activity is being measured. So this is called a Geiger counter, and this is a very common instrument used to detect the beta gamma radiation. And you have now these portable units that you can carry around, and people do use it to measure the radiation in their basements, in old buildings. Radium and radon gas tend to accumulate. Radium from the soil becomes radon gas, and it accumulates in the basement of old buildings. So Geiger counter can be used to detect radiation in pretty much any environment. So what are the units for measuring the radiation activity? It's the Curie, and the Curie is defined. It's got the symbol Ci, capital C, lowercase I, and it's defined as the number of disintegration, specifically 3.7 times 10 power 10 disintegrations per second occurring in 1 gram of radium. All right, so in 1 second, in 1 gram of radium, uh, 3.7 times 10 power disintegrations equals the 1 Curie. All right, another unit of measuring radioactivity is the becquerel, and its symbol is BQ, capital B, lowercase q, and this is the SI unit of measuring radiation activity. All right, and this definition of BQ is it's 1 disintegration per second. All right, so 1 CI is also equal to 3.7 times 10 power 10 BQ. Now, this simply measures the radiation activity, the radiation occurring in the surroundings. But the effect of the radiation on tissue, the biological effect, that is measured by two different units. One is the RAD, which is an abbreviation of radiation absorbed dose, and that measures the amount of radiation absorbed by 1 gram of tissue. So this could be animal tissue or human tissue, so any tissue. REM, on the other hand, is the radiation equivalent in humans. So this is specific for humans, REM, and it measures the biological effects of different kinds of radiation in humans. So, alpha particles, as we talked about before, don't travel much, only a couple of centimeters through the air, and they're easily stopped by clothing. However, when they do enter the body through inhalation, or maybe through a food source, etc., then they cause immense damage inside the body, because the particles are so huge and heavy. All right, so that does lead to organ damage and eventually death in extreme cases. So high energy radiation, however, is able to travel far, and so that causes the most damage, like gamma rays, because they can travel a long way into the body tissue. All right. Beta particles, high energy protons and neutrons can also travel a few centimeters into the tissue, but a very small amount. However, for beta particles, if you use the proper clothing like heavy lab coats, gloves, etc., you can prevent that radiation from penetrating the body. So to determine the REM dose, the equivalent dose, you take the rad, which is the absorbed dose, and multiply it by a factor, and that factor varies from the different kinds of radiation. Alpha particles, the factor is the highest, it's 20. For the high energy protons and neutrons, the factor is 10, and for beta and gamma, that factor is 1. All right. So for beta and gamma, REM is equal to rad because the factor is 1. So a person absorbed 60 millirad of beta radiation. So as I mentioned before, REM and rad are the same because for beta and gamma the factor is 1. All right, so REM is equal to rad. So millirem, 1,000th of a rem, would be equal to millirad, 1,000th of a rad. So 60 millirad is 60 millirem. But what would be the equivalent dose in rems? All right, so we'll have to convert the millirems to rems. All right, so you have 60 millirems, and 1 rem is 1,000 millirems. All right, so you have to then divide this by 1,000. So that's 0.06 rems. All right, so this would be 0.06 rem. Okay, so a person absorbed 50 rad of alpha radiation. What would be the equivalent dose in millirems? Okay, so so you have 50 rad, and it's alpha, and I remember that factor is 20. All right, so that would be 1,000 rad, and so that would be equal to 1,000 rem, and then 1 rem is 1,000 millirem. All right, okay. So the rems will cancel and you'll get your answer, which would be equal to 1,000,000. Okay, millirem. Okay, so that 50 rad of alpha radiation is 1,000,000 millirem. Okay, okay. So the equivalent dose in millirem, that's 1 rem is 1,000 millirem. Now the SI unit for measuring the equivalent dose in humans is the Sievert SV, and that's equal to 100 rems. Okay, so SV is the SI unit for biological damage, and for the absorbed dose, the SI unit is the gray GY, and that is 100 rad. All right, and then one BQ is 1 disintegration per second. One CI is 3.7 times 10 power 10 disintegration per second. So one CI Curie is 3.7 times 10 power 10 BQ or becquerel. Okay. All right, so the FDA has allowed that because certain illnesses are carried by this pathogenic bacteria, the Salmonella, Listeria, E. coli, etc. So they have approved that some foods, like some fruits, can be radiated. All right, and the allowed radiation is zero point 0.3 kilo gray, that's 30,000 rads, and 1 kilo gray, that's 100,000 rad. And the sources for those radiation are cobalt 60 and cesium 137. So the foods are placed on racks, and then the gamma rays pass through the food. They don't harm the food, they just kill the bacteria. And this way, you can see here in this picture, it extends the shelf life. This is um, strawberry that has been radiated, and this is strawberry that hasn't. And so mold starts growing after a few days, whereas the radiated strawberry is able to stay the same. Okay. And so the FDA also places this symbol on packages of food or fruits that have been radiated, so that the public is informed about the choices of food that they want to buy. All right. People who work with the radioisotopes, like in nuclear medicine, have to wear this badge, which is a dosimeter that is able to detect the amount of exposure from all these radiations. So that ensures that they don't exceed the certain allowed level that, and if they do, then they have to take some time off from work before they get back to work. So some of the sources of radiation in everyday life, there's radiation all around us, whether it's from the air, from the sun, the cosmic rays, from the ground. I mentioned radium becoming radon gas and collecting in the basements of old buildings. And then from medical procedures like taking just x-rays and mammograms, etc. Right? They do ask you to limit the amount of x-rays per year, just to reduce the exposure to the radiation from x-rays. And then, of course, from TV or air travel, or even that radon, as I mentioned, in that collects in basements and buildings and so on. All right. So the average person is exposed to about 360 millirem annually. All right. So it's from buildings where we're living, or water, food, air, pollution. More polluted countries have higher levels of background radiation. But the EPA controls the allowed background radiation levels, and so in countries which curb that amount of pollution so as to protect the public, then of course the background radiation is going to be considerably less than in other countries where pollution is uncontrolled. All right. Cosmic radiation is the biggest source of radiation in the background. We'll stop here and we'll continue this in the next video.